All right, good morning, students. Sorry for the impromptu Chem Chat. I just figured I would do it because I've got caught up on my incomplete grades. I'm in a pretty good place, so I figured now would be a good time. And I know that the Bellwork yesterday was kind of difficult, and I figured, we got our test tomorrow. I might as well do some review. So I'm going to use the Unit 4 review to kind of help guide that. Again, the goal is tomorrow. You'll have Vocab 4 and Unit 4 review ready to be turned in. In fact, I should probably create pages for that. I'll make a note. I'll do it in a second. Because your Vocab 4, you'll take a picture of your pages. And I know you're going to be like, oh, it's so much work, but you can do it. I believe in you. If you haven't already, a lot of students have been using the app. It's free on the App Store, and that could be a much easier way for you to take pictures and put them where you want in these pages when you have assignments like that. So anyway, test tomorrow, Unit 4 review due tomorrow, Vocab 4 due tomorrow. But first, I thought we'd take a look at this Bellwork, and hopefully I'm in the right folder. I am not. All right. I need to go here, 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 and hopefully everything will work perfectly. Alright, so here we go. An artificial sweetener has 57.14% carbon, 6.16% hydrogen, 9.52% nitrogen, and 27.18% oxygen. There were a couple of problems that were very similar to this on the worksheet that you had earlier this week that was on percent composition and empirical formula. And the thing is, this takes percent composition, which has already been done for you. You use that to find the empirical formula, and then you use the empirical formula to find the molecular formula. So you can see it all works out. It all works together. So what we're going to do then is we're going to start by following our little poem, which if you don't remember, it is in the notes. So if you took the notes, you should be able to see that. Okay, you should be able to see it. And it says you start by doing percent to mass. So step number 1 is just going to be percent to mass. Okay, that's the first thing we want to do when you're finding the empirical formula. Remember, it's percent to mass, mass to mole, divide by small, multiply till whole is the little poem that you have to remember. And it makes it a lot easier because you're like, oh, well, there's my 4 steps. And so here, percent to mass, literally what we're going to do is we're just going to say, you know what, we had 57.14% carbon. It'd be a lot easier if it were 57.14 grams of carbon. And we're going to do the same thing for all of these, okay? And I need to give myself more room than that because I know what's coming up next. Alright, 6.16 grams hydrogen, 9.52 grams nitrogen, and 27. Wow, that's a great 2, Naren. I'm sure you guys are happy to see that my handwriting has gotten no better in our absence. So we have 27.18 grams of oxygen. So, literally, you just take the percentages and say, you know what, I don't like percentages. I'd rather they were all grams instead. Because when we use grams, then we can use our mole to mass and convert from this into moles, which is step number 2. So step number 2, okay, we want to do mass to mole. Alright, so here we go. Step number 2, mass to mole. Now for this, you're going to need your periodic table. Luckily, you have one, and I have one right here in front of me, and you have the almighty internet, which has more periodic tables than you can shake a stick at. Okay, so I'm going to set this up and say, well, I want grams to be on the bottom, because as you guys have hopefully learned by now, you want to put your unit on the bottom that you want to cancel. So if I have grams and I don't want grams, by putting it on the bottom, that'll cancel it. But what I do want is I want moles of carbon. Now this information, just like normal, you get from the periodic table. So I can look in the periodic table, I can see that the atomic mass for carbon is 12.01, and that just means 12.01 grams per mole. And if I've told you once, I've told you 1,000 times. Per just means for every one, okay, of whatever. And so if per means for every one, then this means 1 mole. So 1 mole is going to be 12.01 grams of carbon. So anyway, we'll do some math here in a second. I want to go ahead and set them all up. So the next one, we'll do the same thing. I'm going to do grams of hydrogen down at the bottom. It's 1.008 grams of hydrogen for every 1 mole of hydrogen. Down underneath, I have nitrogen. And so for nitrogen, Same thing. Grams of nitrogen, which is 14.01. I'm looking at the periodic table, is equal to 1 mole of nitrogen. And then down here with oxygen, same thing. Which you guys have done enough, by now that you probably know several of these. I miss you too, Tony. You probably know several of these without actually having to look at the periodic table, because you get in the habit of looking at it. So we'll have 16 grams of oxygen down here in the bottom. So now that we've got everything set up, we're going to do our mass to mole conversions. It's going to be a piece of cake. So I've got my calculator. Might as well do some calculating. 57.14. Now understand, when you're doing this carbon calculation, yes, technically you're doing 57.14 times 1 divided by 12, but I'm not going to multiply by 1. I know what's going to happen if I do that, so I'm just going to divide by 12.01, and I get 4.75. Okay, so we get 4.75. Now, the units now, they're not going to be grams of carbon anymore. They're now going to be moles of carbon. Okay, just like that. 4.75 moles of carbon. And if you don't believe me, look, grams cancel, and you're left with moles. So everything works out beautifully. I'm going to do the same thing. Wow, that's a loud vehicle. That seems unnecessary. I hope you guys heard that in the microphone. All right, so 6.16 divided by 1.008, and I'm going to end up getting 6.11111111. Okay, so I get 6.11 moles of hydrogen. Do the same thing for the next one. 9.52 divided by 14.01, and I'm going to get 0.67. You know what? I'm going to go and make that 0.68 because of rounding. Okay, so this will be 0.68 moles of nitrogen. Now, I'm going to do my oxygen one. So I have 27.18, and I'm going to divide that by 16. Okay, divide by 16, and end up getting 1 point. I'm just going to go ahead and call that 1.70, or just 1.7, because that's really what it is. Alright, so now that we have all these, we go on to the next step of the poem. So our next step, okay, step number 3, divide by small. Okay, so my next step is divide by small. And I can see my smallest number is this 0.68 down here. Okay, so that is my smallest. So what I'm going to do is I'm going to divide all of them by 0.68. Okay, divided by 0.68. Units don't really mean a lot right here. We're just trying to get the ratio. See, the thing is, even in H2O, okay, if you think about H2O, it just means that there's 2 hydrogens for every 1 oxygen. So we're really just trying to find a ratio, so there's not really going to be any units here. Alright, so let's see, 4.75 divided by 0.68, and I get 6.985. Now here's the thing. When we round that, it's just going to be 7. We're looking for nice, beautiful whole numbers here. And so I'm just going to go ahead and make this 7. So understand, I get 6.985294118, but I know that that's just going to be 7. Next one, same thing, 6.11 divided by 0.68, and I'm going to end up getting 8.98. But again, I'm just going to call that 9. Okay? I'm just going to call that 9. Next one. 0.68 divided by 0.68. I hope you didn't go to the calculator for that one, but we end up getting just 1. And then the last one down here, 1.7 divided by 0.68, we get, dun dun dun, we get 2.5. Oh no, what are we going to do? Mr. Naren, you can't put 2.5 as a subscript. That is correct. So we're not going to do that, because step number 4, let me see if I can scroll over so I can have a little more room. Step number 4 is something else. Let me go to purple. Why not? Step number 4 is we're going to multiply till whole. Now, here's the thing. Because we're looking at ratios here, I'm not going to just multiply the 2.5 by 2 and say, okay, it's 5 now. No, 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 no. Whatever you have to do in order to fix this 2.5, you're going to do to all of them. Okay? So, I'm going to say, well, obviously, if I multiply by 2, that's going to fix this, and I end up getting 5. But because we're looking for a ratio here, I have to multiply all of them by 2 just to keep it all the same. Just to keep it all the same. It's kind of like how if you're making a sandwich, okay, you usually use 2 pieces of bread, unless you're the Big Mac, and then use 3 pieces of bread, which is just excessive. Okay, you don't need 3 pieces of bread. Double-decker sandwiches are ridiculous. But you have 2 pieces of bread. to keep your ratio the same of meat to cheese to bread, you've got to multiply everything the same. So if you want to eat 2 sandwiches, you're not going to be like, oh, well, I'll just have 2 more pieces of bread. No, you're going to multiply everything by 2, so you can have 2 full sandwiches. I've been eating a lot of sandwiches. That's what I'm trying to say. That's all I'm really trying to say. Okay. And so now that we have all of these are the numbers. That's what we're looking for. That's the empirical formula. So I can finally write my answer, and I'm going to write it, I guess I'll write it up here. So all of these, okay, are going to end up making my formula. So carbon, it's going to have a 14 underneath it. Next, we have hydrogen. Hydrogen's going to have an 18. Nitrogen, it's going to be a 2. And oxygen, that's going to be a 5. And so this is my empirical formula. That's my answer to part A. Now, I've had some students ask me and say, you know, Mr. Nair, when we're doing these, do we have to get it in the right order? Like, what if the H comes first? What if the N comes first? Unless it's an acid, and acids put H first, we really don't care too much. They would never trick you like with something like that. Not like we have final exams anyway, but I would not trick you with something like that. I'll put it in the right order. So if you had a multiple choice problem, it would always be CHNO. I wouldn't make one of them ON just to trip you up. Okay. So anyway, there's our answer to part A. Let's take a look at part B. So part B over here, it says the molecular formula. If the molar mass was determined to be that huge number right there, daggone, that's a lot of grams per mole. So the thing is, whenever you're doing these molecular formula type problems, okay, so now we're working on part B. Whenever you're doing molecular formula type problems, you're going to end up having your empirical molar mass, okay, and you're also going to have your experimental molar mass. So that means, like, in a lab, they determined the molar mass to be, you know, whatever it is. And for this problem, they're giving it to you. And so for empirical molar mass, you might be thinking, well, how do we get that? Where's that going to come from? Well, you just found what the empirical formula is, this C14H18N2O5. And so you can find the empirical molar mass. Now, it's not going to be fun, but you can still do it. And see, as you can see down here, I've already made my equation. And if you ever get confused and you're like, well, which one goes on top, which one goes on bottom, you're looking for a whole number here. So your bigger value, okay, needs to go on top. And typically that's going to be the experimental, because otherwise it would be really weird. So it'll make sense when we do the math here in a second, but your bigger number is going to be on top. So in fact, I'm going to go ahead and write that in. We know that my molecular weight that they give me for part B, they said it's 882.90 grams per mole. And I'm dividing by my empirical molar mass. And yeah, this is going to be kind of annoying. So what I do is I say, well, I got 14 C's. So we got 14 times, so this is my one for carbon, and that's going to be times 12.01 grams per mole. Okay, so carbon, 12.01 grams per mole. Next thing, I'm going to add all these up here in a second, so just give me a second. We need to do hydrogen, and so hydrogen, we had 18 of those. This is going to be 18 times 1.008 grams per mole, and we'll get a number here in a second. Next, we're going to do nitrogen. There's only 2 of them, but we still have to do 2 times the molar mass of nitrogen, which is 14.01 grams per mole. And then finally, we have oxygen. So there's going to be 5 times my 16.0, wow, that's a good 6, there we go, grams per mole. Alright, let me do some math real quick. And yeah, you could do all these in the calculator at one time if you're really creative and careful with your parentheses, but I'm going to do it in separate steps just so you guys can check your numbers and make sure you're getting what you should. And who knows, maybe I would have made a mistake if I tried to do it all in one go. We don't know. I'm not perfect. And yeah, these do have units, but I don't really care right now. We know it's all going to be grams per mole. We'll fix it in a second. Okay, next I have 18 times 1.08, and I end up getting 18.144. Then I'm going to do 2 times, you know what, I probably don't need that. It's just going to be 28.02. There we go. And then the last one, 5 times 16. I end up getting 80. Okay, and so we're going to add all of these numbers together. Okay, and that'll be our empirical molar mass. Remember, empirical is the smallest way you can write the formula. These numbers right here cannot be made any smaller. See, 5 is going to prevent everything. And so unless everything was divisible by 5, you cannot simplify this any more than you have already. So that's what we mean by empirical. So I'm going to add all this junk together. I'll be right with you. I'll be right with you. And I get 294. Let's just make it 0.3. There's no need to make this any bigger than that. And the units, I know I dropped it off a little bit there, are going to be grams per mole. So the thing is, this number is going to go over here. It's going to go in the bottom of this division that we're doing over here. So I'll put 294.3 grams per mole. Notice grams per mole are going to cancel. So we technically have no units here. And that should make sense because we're looking for just a number. We're just trying to find out, okay, what have I got to multiply everything by? So when I do this in my calculator, I get 2.99999 and several other 9s. But we're just going to make that 3. So what this ends up equaling is 3. That is not the answer. Okay, that is not the answer. They're looking for a formula. It says over here, molecular formula. So we've got the number that we need to multiply by, but we're going to multiply our equation from earlier, this C14H18N2O5 times 3. Okay, we want to multiply it times 3 because that'll tell us what the molecular formula is. Molecular formula is not the simplest. All right, so what I'll do really quick is I'll say, okay, well, we got C14H18N2O5, and I'm multiplying all the subscripts, all 4 of these, by 3. Okay, and so let's see what we end up getting. Okay, 14 times 3, I get 42. Okay, 18 times 3, I get 54. Next, 2 times 3. I'm not going to do that in my calculator. I almost did. I got 6. And then last, I'm going to have 15. So this, thanks for what, person? So here's going to be our molecular. Oh, no, you can't see it. I was doing all that work, and you guys can't see anything. So this is my molecular formula. And that's the answer for part B. So as you can see, there's quite a bit to this problem. That's why I wanted to go over it. So there's the full solution, okay? But that's what I wanted to go over. Because as you can see, part A has a lot to it because you got to go through the whole empirical formula method using the poem, using the 4 steps, and then after that, you have to do just a little bit of work to find out what the molecular formula is. So anyway, there you go. So I hope that was helpful. All right, next we're going to take a look. Not at that. Where did I put this? There it is. Next, we're going to take a look at the Unit 4 review. And if any of you that are here in the video, how many people we got? 4 apparently. If you have any questions, just slow me down. But otherwise, I'm just going to kind of roll through it. All right. So I need to go here. Here we go. That's what I want. That's what I want. Alrighty. This is not going to be that bad. I just feel like I should go over it because I have a feeling I'm going to get a lot of questions today, and I'm going to really enjoy saying, well, did you watch the video? And the person's going to say no. So anyway, first part, we just got to fill in the blanks. According to collision theory, molecules is the answer here. Molecules must collide in order to react. Yeah, according to collision theory, things have got to bump into one another in order to react at all. They must collide in the correct or appropriate orientation. Okay. Cross that out. And with sufficient energy to equal or exceed the activation energy. Now, we actually did talk about this before all this remote learning began. But basically, activation energy is the energy you need for the reaction to happen at all. Okay, if you remember, there's a little bit of a bump to it. I'll draw my table over here. So, like, if it needs to look like that, okay, this little bump right here is the activation energy. And the best way to show it is, remember, when you light a match, the match gets really, really big, and then it calms down a little bit. So that's the activation energy. A catalyst. Okay, that's our last thing. A catalyst can be used to lower the activation energy required for the reaction to take place. So really what that catalyst does then is it actually lowers that a little bit. It flattens the curve. That's something you guys have probably heard a lot lately. That's something else. But in terms of chemistry, it lowers that little curve so that it doesn't take as much energy, and therefore reactions are going to take place more quickly. Identify the 5 ways to tell a chemical reaction has taken place. Well, we took notes on this, so this is straight from the notes. So in fact, I'm going to read it to you. I'm going to go back and find it. So if I go back to Intro Chemical Reactions, how to tell? Well, thing number 1 is bubbles. It's literally what I wrote. Okay, so gas produced is going to be this first thing. Gas produced. So in other words, you get some bubbles. Good example of this, like I've told you guys, is a baking soda and vinegar volcano. It makes lots of bubbles because there's a reaction taking place. Next thing that we're looking at is energy change. So that means you're going to have heat or light. Okay, so we have energy change. Again, this is coming straight from the notes, which if you guys have been doing, no, there's a couple people, I think they're just lurking, Tony. So the thing is, an energy change means you're going to have heat or light. Sorry, what I was going to say is this is coming straight from notes, so if you guys have been taking notes when you're supposed to, according to lesson plans, this shouldn't be anything new for you. Thing number 3, I'll go back and read it from the notes again. It says solid forms. In other words, you're going to have a precipitate. Okay, a solid formed. And we've talked quite a bit about precipitates at this point. Okay, next thing, you can have a temp change. So sometimes it can get really hot, sometimes it can get really cold. An endothermic reaction, we're going to talk about heat soon, but an endothermic reaction is where it actually feels cold. And then thing number 5 is a color change. Okay, we saw one of these in a reaction that we did one time where it turned bright yellow, but a color change is something you're looking for. Alright, next thing. Part of chemistry is testing for the products of a chemical reaction. Determine how a burning splint and or lime water can be used to test for each of the following. So this is something that is from the standards, but it's so specific I don't really feel like it's worth mentioning. So like the standards specifically say, you know, oh, well, they need to know, like, what happens if you put a burning splint in oxygen? What does it do? What happens if you put a burning splint in carbon dioxide? You can find videos of it online. You can just type in, I think, gas tests, you know, burning splint gas tests, and you'll probably find it. But the idea is you have this splint, okay, which is just a wood stick. Think about like a skewer, like a kebab skewer. At the end of this, they have a little flame. Okay, there we go, a little flame just like that. And the idea is if you put it into a test tube, scroll up just a little bit. So if you put it into a test tube that maybe has oxygen, maybe it has hydrogen, maybe it has CO2, like it'll do certain things. And the other thing is with lime water, which honestly, if you're watching this video and you're paying attention, you can just cross that out because it's dumb. Lime water does react with carbon dioxide, but I don't care. Let's just focus on the burning splint. So oxygen gas. Oxygen, as you hopefully know, is necessary for combustion. So if you have a tube that's filled with pure oxygen, the burning splint is going to flare up. So it's going to burn stronger, brighter, whatever you want to say here. / brighter. Hydrogen gas. Ooh, that's brighter. That's not what I'm trying to say. There we go. Or hydrogen gas. Hydrogen gas is actually explosive. So hydrogen is not going to just burn brighter. It's going to actually make a popping sound because it explodes. Now, it's not a huge explosion. We're talking about a test tube here, okay? So not a lot of gas. But because it all reacts at one time, it does make a loud pop sound, okay? So it's like a pop, like that. Yeah, that was an excellent example. Next, we have carbon dioxide. As you guys hopefully know, carbon dioxide is a product of combustion. So carbon dioxide is not going to help it burn. It's going to make it go out. So flame goes out. Whenever we have candles, you know, here in the apartment or wherever, if you ever have a candle, one of those ones with the glass lid, you got your little wick burning on the inside. But the thing is, instead of blowing it out and getting smoke everywhere, if you actually would just put the lid on this, then when you do, it goes out because all the oxygen gets burned up and turned into carbon dioxide, and you can't burn with carbon dioxide. It doesn't happen. Moving on. List each of the following as an example of a chemical or physical change. You got it. I'm hoping this was really easy. From what I've seen so far on the Unit 4 review, I don't think anyone has had any difficulty with it. Cutting or grinding. Well, that's definitely going to be physical. Okay. Remember, the question you need to ask yourself when you do this is, hey, Emily, good morning. The thing you have to ask yourself is, physical change, it's still going to be the same thing. Okay, so if you take water and you put it in the freezer and you freeze it, it's still H2O. So that's still just a physical change. Alright, effervescence, which if you guys don't know what effervescence is, that's where you got like an Alka-Seltzer tablet. Okay, and you put the Alka-Seltzer tablet down in some water and it bubbles. Okay, if you don't know what Alka-Seltzer is, well, I don't know what to tell you. But effervescence is going to be a chemical change. It's creating bubbles. Okay. It's creating bubbles. Next one, dissolving. So, dissolving, I would argue, is really just a physical change because you can undo it. For instance, if you have NaCl and you put that in water, it's still NaCl, it's just Na plus and Cl minus. Okay? But it's still there. But then again, a bond was broken. So honestly, if you wanted to put dissolving in the middle, that's fine. I think I'm going to put it over here. Okay. Next, we have a phase change. I just gave you an example of one. You put water in the freezer, you freeze it. That is a phase change. It's going from liquid into solid water. But when you do that, it's still water. So phase change is going to be a physical change. Corrosion. So corrosion can happen with not pure silver, but if you've ever seen sterling silver in jewelry, or copper, or pewter, whatever, certain metals are going to corrode where they're not as shiny anymore. And really, that's just rusting. It's just rust. It's combining with things you have in the air, and it's corroding. So corrosion, it is a chemical change. So I'll put that over here. Morgan. Sorry, Mrs. Nairn is here. Dissolving, physical or chemical?
Physical.
Okay, I was right.
If you can separate the two components, it's a physical change.
Yeah, but you end up you can put them back together too, because if you just
if you can separate or put them back together, it's physical.
Yeah. Okay.
You can separate dissolving something by boiling off the liquid.
Okay, that's enough. Thank you. All right, so we have corrosion, oxidation. It's another name for rust. Rust that most people think of is really just iron oxide. Okay, or iron 3 oxide, whatever. But that's still just combining with oxygen. That's making rust, but it's still a chemical change. Okay, so put that over here. Compressing means like you take air and you compress it. Yeah, that's definitely going to be physical because it's still the same stuff. It's just a lot I just wrote down physical. Golly. But it's still just closer together. So compressing, definitely going to be over here. And then burning, definitely going to be over here with a chemical change. Alright, definitely going to be over here. Alright. Okay, fine. Morgan, they want you to teach them something. So here, come teach this little section right here. I'll let you pick. You can talk about this. Actually, no, you do the whole page. Here you go. You write on here, and it shows up there. Introduce yourself.
Okay, so...
Introduce yourself.
I'm Mrs. Nairn.
That's right.
And I also teach chemistry. Okay. Alright, so I'm looking at the table that says hydrocarbon, salt, and hydrate. Okay, and so you have to choose which word best describes that definition. So an ionic compound that results from an acid-base neutralization, I know Mr. Nairn talked to you about this, was a salt.
What makes it a salt?
And a salt is just an ionic compound that forms as a result of an acid and a base reacting together. And it's not just NaCl, by the way. It can be anything ionic, metal and nonmetal, or polyatomic ion. Okay, the second one, a compound that consists primarily of carbon and hydrogen. That should make some kind of sense, given the words there, is a hydrocarbon.
Yeah, really tough one right there.
That's going to be from your combustion reactions. All right. And the last one, by process of elimination, has to be a hydrate. But if you think of the word hydrate, it kind of makes you think of, you know, water. So, and if you see a hydrate, it's going to be an ionic compound that has a little dot beside it and then like 5H2O. That's all a hydrate is. Don't let it freak you out. All right, cool.
No, do the second table.
The second table. Okay. So acid-base neutralization reaction. The required reactants. So don't think too hard. It's going to be an acid.
They haven't learned acids and bases yet.
And it's going to be a base. That's going to be your reaction. Yes. Okay, Emily is on top of it apparently. Okay, the products are going to be kind of what I talked about already. One of them is going to be a salt. And the other one is going to be water, because what an acid and a base do, because they're opposites of each other, is they neutralize each other. Okay.
Example.
An example, I'll give you an easy one.
Do it down below. Don't do it. You can't fit it in that box. Do it in this space.
So I'm going to do it in the space below here. All right. So an acid is something like HCl. What's it?
It'll load. Go ahead.
And then a base is something like NaOH. I don't know if Mr. Nairn taught you this, but acids.
I told him acids always have an H in front.
Yeah. Acids always have H in the front. Bases always have OH in the back. That's kind of how you remember it. Okay. So when this is just a double replacement reaction, so if you check on your reference tables, you'll see that, you know, it's AB plus CD equals AD plus CB. Okay, so that means that hydrogen and hydroxide are going to come together, and that makes HOH, or in other words, water. Okay. And then sodium and chlorine are going to come together, and when you put those together, you get a swap and drop. Yeah. So you're going to end up with NaCl, because they're both positive 1 charges. Positive and negative 1 charges. There we go. So there you go. There's your example.
And then type of reaction, just write double.
All right. And then I've already said this, but this is a double replacement. There you go. All right. Hope that helped.
All right. Thank you.
All right.
I mean, that was a very mediocre job. I'm just kidding. I'm just kidding. I'm just kidding. All right, but anyway, there you go, guys. What I think of when I teach you guys this is, oh yeah, you need to get the type tisk. So this is gonna be a type B. Guys, the way that I like to talk about it is when you're doing acids and base neutralizations. Think of it as like hot water and cold water. If you mix the two together, you get water that is room temperature. So think of neutral as being room temperature. Okay, Tony. I'm assuming that is coming from a very nice place that you said that. But there you go. Let's take a look. And yes, double replacement, but double replacement type B. I make them be very specific because I'm mean. But double replacement type B is acid-base neutralization. All right, whatever. Let's move on. Identify the following as synthesis, decomp, single rep, double rep, or combustion. And I am going to be really specific here, but obviously, because I didn't ask for it in the instructions, you don't have to be specific with types, but I do think it's good for you. So looking at this first one, you can see that we start with two things, and then you combine them together into one thing. Gee, I wonder what that's going to be. Probably synthesis. Okay, this is going to be a synthesis reaction. And if I look, I can see this is actually synthesis type A. Okay, because you start with two things, okay, just two separate elements. Iron is an element, oxygen is an element, and you combine the two together. Next, we have CH4. CH, okay, carbon and hydrogen. So that's going to be a hydrocarbon. Okay, it's going to be a hydrocarbon plus oxygen, and then you end up getting some stuff. So guys, you should know this is just combustion. Don't overthink it. Moving on, next one, we have 4 things. So I've told you. If you see 1, 2, 3, 4 distinct things, okay, nitrate here, it's a polyatomic ion, but it's still one polyatomic ion. If you have 4 distinct things, you know you're looking at double replacement. The only other thing that I want you guys to check is just look, do you have any acids or bases here? And when I'm looking at it, I don't see any acids because there's no H's anywhere, and so I know this is going to be double rep type A, and that's all. Next one, problem number 4. Okay, we have 2 H2O2, and so you're starting with one thing, and then it becomes 2. So remember, when it breaks down into smaller pieces, we know we're looking at decomposition. Okay, we'll look at decomposition, and then we got to see, is there a specific thing that we can use here? And I'm not seeing one. No. I mean, I guess no. See, the thing is, it doesn't really fit into any of these molds. Hydrogen peroxide. Hydrogen's acting like a metal, but it's not a metal. So when I'm looking at this, I think I would just say decomp, just type A. We'll just say type A for now. But that one's kind of weird. I'm not sure why Perugini picked that. It's not a specific type. H2O2 goes to H2O plus O2. Because the thing is, this would look like a metal, you know, a hydroxide.
I would say A binary, but it would have been H2 plus O2.
Yeah, I know. I think Perugini did a typo. Doesn't matter. Let's look at number 5. Alright, number 5, we have Mg plus 2HCl, and as you can see, we have some single replacement stuff going on. We can see that Mg is pushing out the H, okay? It displaces the H, and so we know it's going to be single rep. Okay, but we need to see which type of single replacement is it. This is replacing hydrogen, so we know it's either going to be B or C, and it's replacing it from an acid. HCl is the acid that you guys probably know about, hydrochloric acid. Okay, so here, Mg is going to push out the H from an acid, so it's going to be a type C. Alright, moving on. Given the reactants, okay, we're going to predict products, oh boy, balance each equation, and then we got a couple other things to do. So if it's going to be single replacement, we're going to use the activity series, okay, to determine if the reaction would take place. Okay, so reaction yes or no. Or, okay, we're going to, if it's a double replacement, we're going to determine if any product will form a precipitate. Okay, so we got to determine if it's a precipitate or not. So again, if it's single replacement, we do one thing, double replacement, we do another, but we have to predict products for everything. So let's go ahead and begin with that. Alright, so zinc plus HCl, this is actually going to be the type we were just looking at. This is just going to be a single replacement type C. The instructions don't ask for it, but I'm going to write it over here just for your convenience so you can see that. And so, based on what I see, I need a piece of paper. Based on what I see for single rep type C, we know we have a metal plus hydrogen bonded to something. Okay, in this case it's Cl, and it's going to become now the metal bonded with Cl plus H2. Okay, I'm looking at it straight from my list. So I could label everything, but I don't think I'm going to. So I'm going to end up bonding Zn with Cl. Okay. Now the annoying thing here is we actually don't know what the charge on zinc is, but what is the charge on zinc usually going to be? 2. All right. Tony, we'll turn it in. I'll probably give you, Tony, if you guys can't see the comments, you should be able to. I think it's in the screen. But Tony is asking, how do you turn in vocab? I'll give you more information on it tomorrow, but basically I'm going to create a blank page in your Unit 4 folder that's just called vocab turn-in or vocab submission, and you guys can use your cameras to take pictures of your vocab and turn it in on there. Highly recommend if you have the app on your phone. It's a free app. Get the OneNote app. It's a lot easier to use the camera on your phone than it is to use the camera on your computer. Okay, so anyway, we have Z and CL. But the issue here is you can't just slap them together. Hopefully you guys remember you have to swap and drop. So what we'll do then is we'll say, well, zinc is going to be +2, chlorine is going to be -1. And if you don't know how to do that by now, I pity you. The 1 goes down there, the 2 goes down there, so we get Zn with a 1, Cl2. Alright, so you gotta do swap and drop. I'm also going to leave some room for a blank. And according to what the formula says, we're just going to have H2. We know that 2 goes there because it's Brinkelhoff. So we got that, we're good, we're ready to go. Alright, I'm just going to go ahead, well, I guess we can go ahead and balance it. I was going to say, you know, maybe we should just do all the predicting first. We can go ahead and balance it. This one's not very difficult. I don't really have a lot of room to make a list either. I can squeeze it in. So we have Zn, we have H, we have Cl. I have 1 and 1, 1, 1, 2, 2. And so as we can see, the way to fix this is just to put a 2 right here. And by doing that, it makes it so we have 2 of each. So there we go. So we predicted products, we balanced it, and now we have to say, well, if it's single replacement, which it is, we need to use the activity series to determine if the reaction will take place. And remember, I've told you before, above will shove. And so that's what we have to look at if it's single replacement. So I'm looking at my activity series on here. I'm trying to. I got to flip to it. And I'm looking for zinc. I found it. And it says zinc will replace hydrogen from steam, and zinc will also replace hydrogen from acids. Okay, so I can see that it is within that range. You'll see there's kind of an arrow there next to replace hydrogen from acids. But yeah, zinc is definitely above. So will it happen? Yes, of course it will. Yes. Moving on to number 2. I'm going to go a little more quickly this time. This is a double replacement reaction, so that means we're going to swap and drop new things. Okay, so that means Ag was bonded with NO3, but now Ag is going to bond with Cl. So I'll go ahead and write it. But as you guys know, we've got to swap and drop. We can't just slap them together. Okay, plus now we're going to have zinc. Zinc was bonded with Cl. Now it's going to bond with NO3. Okay, zinc here had a charge of 1. How do I know that? Well, do multiply down, divide up. I'm going to do it on both of these. Let me zoom in just a touch so you guys can see what I'm doing. That's a little too much. And by the way, this is double rep. I know we don't care, but this is double rep type, just type A. Okay, so multiply down, divide up. I know it's been a while. NO3, I can see the charge on that is going to be a -1. So I'll put that there. Ag, we don't know what the charge is, but we do know there's a 1 written down there. Now remember, we're not going to multiply by 3. When we do multiply down, divide up, we don't want to multiply by the 3, because if I look at my polyatomic ion list, I can see that the 3 is a part of it. So really what we're looking at here is we're looking at 1 NO3. And so when you end up doing all this, multiply down, okay, we get 1. Divide up, we get a 1. So we know this is silver with a +1 charge. And as you can see, I've written it over here because I'm going to need it to swap and drop here in a second. I'm going to do the same thing for zinc. Okay, because I got to find out what the charge on zinc is. Cl has a 1 below, zinc has a 1 below. Charge on Cl is always a -1. So 1 times 1 gives me 1. Okay, 1 divided by 1 gives me a 1 as well. So hey, here, zinc has a +1 charge. It's usually a +2. But we'll just go ahead and give it a +1 for this one. That is okay. And if it's not, we'll know because it won't balance correctly. But anyway, it works out. So what that means then is we actually need to swap and drop these. So Cl still is -1, and 3 is a -1. So hey, when we swap and drop all the ones in this problem, they do end up being just 1s down below. And obviously we don't need to write that. And also, I can tell it's already balanced. If you don't believe me, look, Ag, NO3, Zn, and Cl, and that is going to be in the way of the next problem. Let's find a better place. Ag, NO3, Zn, and Cl. On the left we have 1, on the right we have 1, 1, 1, 1, 1, 1, 1. And so everything is already balanced, so we don't need to do anything. Sorry, because that's kind of sloppy. Alright, now this is double replacement. And so for double replacement, I told you guys you need to determine if there is a precipitate. So what I'm going to do, luckily I left myself a little bit of room, is we have to figure out, is it going to be solid or is it going to be aqueous? Okay, so what I'm going to look at is my solubility rules. I'm flipping to it right now. So I got my solubility rules in front of me. I'm going to take a little sip of Cheerwine. That's our sponsor for today, Cheerwine. And I'll be right back. Hold on. That is carbonated. Alright, so anyway, looking at my solubility rules on here. First thing we're going to look at is chlorine. Okay, so we're looking for chloride rules, and as I can see, in the soluble list, okay, in the soluble list, it says all chlorides are soluble except silver. So I'm going to say that again. All chlorides are soluble except silver. And so that means it's insoluble. And so if it's insoluble, that means it's a solid. So I'm going to put an S there. Okay. Next, we have zinc nitrate. Okay, we have zinc nitrate. I'm going to look for rules on nitrates. It says all nitrates are soluble. Period. If it is a nitrate, it is going to be soluble. And so if it's soluble, you guys hopefully know, you write an AQ there. It just means aqueous, which means it does dissolve. So our precipitate, yeah, it's going to be AgCl because it is a solid. It will not dissolve into water. Alright, moving right along, let's take a look at number 3. And if you guys do have questions, slow me down, but otherwise I'm just going to keep on rolling. This is definitely going to be a single replacement. This is just a metal replacement. Yeah, so this is a type A. Hope you guys can hear the sirens through the internet. I'm glad you had some Cheerwine to sip on. It's delicious. So single rep type A. And so my replacement, remember, it's metal to metal replacement. So where are my metals? Aluminum and iron. So that means aluminum is going to push out iron and combine with oxygen. So let's just see what happens. So I need to have Al bonded with O. And remember, don't just slap them together. Alright? Charge on aluminum. Hopefully you're looking at your periodic table and you're saying, oh, aluminum is going to be +3. Alright, next I hope you're saying O. Oh, well, O is going to be -2. So when you swap and drop, 2 goes down there, 3 goes down there. Alright, so make sure you know that you're swapping and dropping correctly. I'll leave myself a little blank. Next, we're just going to have iron all by itself. Poor, lonely iron. Alright, and so iron's over there because it's not bonded. It just got replaced by aluminum. Let's go ahead and balance this real quick. I think I can fit it in. So Al, Fe, and O. There's 1 aluminum. There's 2 aluminum on the right. There's 2 iron on the left. There's 1 iron on the right. 3 and 3. Alright. So yeah, this is pretty easy. If I put a 2 over here in front of Al, that makes it so I have my aluminums fixed. If I put a 2 over here in front of Fe, that means I get my irons fixed. So pretty easy. Balanced. Now, this was single replacement. So the question we have to ask is, will it react at all? Okay, we need to determine, will this reaction take place? So again, I look at my activity series, and I'm looking for iron and aluminum. And as I can see, aluminum is higher on the list than iron. So, will aluminum shove out iron? Yes, above will shove. So again, I'm looking at my activity series in person. Here's paper. You guys have the copy of the green sheet in your general folder, so you can find this too. But because aluminum is higher, above will shove. Yes, reaction will take place. Alright, last one. It's obviously double replacement, but this is actually going to be a double replacement type B. How do I know that? Well, here's an acid. Here's a base. I know that because acids have an H out front, bases have OH on the back. So we know water is going to be one of the products. We just talked about this not too long ago. So it's just going to be liquid water. And the other thing is going to be that ionic compound, okay, the salt, that neutral ionic compound. And what's it going to be? Well, we're going to have Na bond with SO4. Na is going to bond with SO4. I'm going to do my swapping and dropping over here just to keep it out of the way. Na has a +1 charge because it always does. SO4 has a -2 charge. Okay, so I'll put that right there. So the 2 is going to go down below Na. The 1 goes down below SO4. So what do we get? Na2, SO4. Just like that. Just like that. All right. So let's balance this thing real quick. H, we have SO4, which I do want to keep together. We have Na, and then we have O. H's, on the left we have 3 of them. On the right we only have 2. If you don't see where those 3 are, I mean look, you got 1 H right here, and you have 2 H's over here in front of the SO4, and that's sulfuric acid. SO4s we got 1, on the right we have 1, NA's on the left I have 1, and on the right I have 2. O's on the left I have 1, and on the right I have 1. And before you say, but Mr. Aaron, what about those 4? Okay, what we can see is that because the O is combined within the sulfate, we're only going to count that in the sulfate. We're not going to count it a second time. So anyway, what I'm going to end up doing, I think I'm just going to put a 2 here and see what happens. If I put a 2 in front of sodium hydroxide, that's going to change a lot of stuff. Na is now going to be 2. H's are now going to be 4. Alright, and I know that's a little sloppy down there, but that's what I'm doing. And O's are now going to be 2. It's not a big deal. Putting a 2 here is going to fix it. So if I put a 2 in front of the water, 2 times 2 is going to give me 4. 2 times O is going to give me 2. That's a 2. There we go. Balanced. Okay. Now, if you're wondering how I knew that it was a liquid, H2O liquid, it's just because water is liquid at room temperature. And if you're saying, well, don't you need to do solubility rules? Isn't it an oxide? No, 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 no. Guys, you can't dissolve water into water. That's not a thing. Alright, so you can't dissolve water into water. And so for that reason, you just make it liquid. Alright, so next thing that we got to do is we've got to figure out if Na2SO4 is going to be soluble or insoluble. So once again, I'm going to go back to my solubility rules. This is double replacement. Double replacements, you usually have to find this out. Are you going to have a precipitate? Okay. I do miss that, Emily, because yes, it would be like perfectly quiet, and then all of a sudden you'd hear like and you try to do it so quiet too. Alright, so sulfates. Where are my rules on sulfates? Here it goes. It says all sulfates are soluble. And it doesn't say anything else about sodium. So all sulfates are going to be soluble, so it's going to be AQ. So are there any precipitates? No. There are no precipitates for this. There's no solids. And before you say, well, yeah, but liquid's not aqueous. I know, because it's liquid. But it's not going to be a solid precipitate. Alright, let's move on, because we got a lot to cover. Short answer. Using the balanced chemical equation below, answer the following questions. Boy, that was nice of him. It's already balanced. What is the stoichiometry of the chemical equation above? Guys, stoichiometry, as I've told you, is just a fancy way of saying mole ratio. It's just a fancy way of saying, you know, conversion factors. So really what we're looking at here is we're trying to find what are the different, you know, ratios that you can make. And there's only so many combinations. We have 2 products, 2 reactants, 1, 2, and we have 1 product, 3. So there's only so many different ways to write this. So for example, first one I want to write, put Fe, sorry, I'm going to write that as moles. I want to go back to my red anyway. Moles of Fe. And let's go ahead and compare moles of Fe to moles of O2. And we're also going to want to have one that compares moles of Fe to moles of Fe2O3. That's another one we're going to want. And then the final combination that we're looking for is we want to have moles of O2 compared to moles of Fe2O3. So the thing is, stoichiometry is just mole ratios. There are only 3 combinations. And before you say, well, Mr. Aaron, shouldn't you be, flip it? Because shouldn't you have O2 over Fe? I'm not bothering, okay? It's not worth it. It's the same thing. It's just flipped over. This is what I'm looking for here. So, whenever we're doing this, you have to use that chemical equation. So moles of iron, it's going to be 4 moles of iron for every 3 moles of O2. Next thing we're looking at, moles of iron. Well, it's still 4 moles of iron from the chemical equation for every 2 moles of Fe2O3. And the last one, 3 moles of oxygen for every 2 moles of Fe2O3. So this one right here, I have a feeling a lot of people are going to be confused with just because they don't really know what I'm looking for. That's what I'm looking for. That's what I'm looking for there. Number 2, if you were given 4 moles of iron, all right, pause. They're giving us something. They're starting us with something. So we're starting with 4 moles of iron. How many moles of oxygen gas are required for the reaction to take place? So we're looking for moles of O2. That's what we're looking for. They're giving us a target. So I'm just going to do a conversion really quick. It's not super complicated. I want to get rid of moles of iron, so I'm going to put that on the bottom. I want to get 2 moles of oxygen, so I'll put that up on top. And hey, moles of O2. And so, hey, we look at my chemical equation. I can see, well, for every 4 moles of iron, I need 3 moles of O2. And so, obviously, if you guys haven't figured it out already, you just do the math. 4 times 3 is going to give you 12. Divided by 4 is going to get you back to 3. But 3 moles of O2 is what we're looking for there. Okay, that's what we're looking for there. Number 3, this one's a little bit different. Given 50 grams of iron. Okay, given 50 grams of iron. And once again, they're giving us something to start with. How many moles of oxygen are used? So we're still looking for moles of oxygen. Way over here somewhere. That's what we're trying to get to. But you can't just go from grams to moles. Grams of iron to moles of oxygen. You got to get them both in moles first. And so that's what we're going to do. So my first step is I don't want grams of iron. That's useless for this problem. I want to get moles of iron. Everything goes through moles, guys. You've got to go through moles. And so if I look at my periodic table, I can see that, well, for 1 mole of iron, what's the molar mass? 55.85. Okay, 55.85 grams of iron. All right, there we go. Now it's loaded. But if I were to stop right there, yes, we'd cancel out grams, but we would be stuck with moles of iron. I don't want moles of iron. I want moles of oxygen. So I need another conversion factor. Put moles of iron on the bottom. Put moles of oxygen up on top. And that is going to fix everything out. We're going to use the same ratio as before. 4 moles of iron for every 3 moles of oxygen. And again, where did that come from? How did that? Seriously? Where did that come from? This equation right here. It came from the balanced chemical equation up above. So that's where those numbers are coming from. So again, moles to mass, use the periodic table. Moles to moles of something else, use the chemical equation. So when we do all this, okay, that cancels out everything that we don't want, and it leaves us with what we do want, which is moles of O2. So I'm going to do some math really quick if I can find my calculator in this pile of papers. There we go. So 50 divided by 55.85 times 3 divided by 4, and I get 0.67 moles of O2. I'm going to put a box around it. Always box your final answers, please. If you're watching this right now, please please do that. All right, given 50 grams of iron, how many grams of iron 3 oxide are produced? All right, so we're doing something similar. Actually, we're not doing something similar. We're practically doing the same thing, but instead of looking for moles of something, we need to find grams of something else. So this last one is the hardest one. They're still giving us something to start with, 50 grams of iron, but now they're saying, look, how many grams of Fe2O3 are we going to end up having? So we got a ways to go. We can do it. First step, go from mass into moles. Remember, we're going from iron into iron oxide. We're going from something to something completely else. So, something else completely. So we're going to have to go through moles first. So here we go. First step, same as before. I want to get rid of grams, so I'm going to put that on the bottom, and I want to get into moles, so I'm going to put that up on top. Then I need to go from moles of iron, because I'm trying to get rid of that. I'm going to put it on the bottom. There it goes. And I want to get to moles of Fe2O3. So I'm going to put that up on top. And once again, I look at my formula up here, and I can see, well, for every 4 moles of iron, okay, I have 2 moles of Fe2O3. Okay, it's coming from that chemical equation up there. All right. Then think about what we'd have if we stopped right here. Look, we started with grams of iron, canceled it. It went away. And we had moles of iron. But then we said, no, I don't want moles of iron. Canceled it. Got rid of it. But if we were to stop right here, we would have moles of iron oxide. But I don't want moles. I want grams. And so to get grams of iron oxide, we've got to do one more conversion. Okay, where we're going to put mole on the bottom. Okay, so, wow, that looks great. 1 mole of that. But we need to find out how many grams then. How many grams is that going to be? And so to do that, we've got to do one extra little step. We've got to find out what that molar mass is. I'm going to do it over here to the right. So here's the thing. In this, okay, we have 2 irons. So that means I'm going to do 2 times 55.85 grams per mole. And I have 3 oxygens. So I'm going to do 3 times 16, there we go, grams per mole. And I apologize for my handwriting. I know it's atrocious. All right, load, there we go. All right. And so we're going to add those 2 together. That's going to end up giving us our molar mass for iron 2 oxide. Give me just a second. And I get 159.7. So this is 159.7 grams of iron 2 oxide, sorry, iron 3 oxide per 1 mole, okay, of iron 3 oxide. So that number over there, it's going to go right here. Okay, so again, this is just from the periodic table. So you can use that from the periodic table. All right. So anyway, now we can do all our math. We can see moles is going to be canceled. And so we end up getting everything canceled we don't want, and we're left with what we do want. So now I have to do a little bit of math and find out what we're going to end up getting. So I'm going to start with 50 grams times 1. I'm not going to do that. Divided by 55.85 times 2 divided by 4 times 159.7. Okay, and I end up getting 71. I'm just going to call it 71.5 grams of that right there. And so there we go. There's the answer to that problem. So as you can see, in problem number 2, not that bad. I mean, we're just going from moles to moles. Problem number 3, we started with grams to go to moles of something else, so it's a little more difficult. But problem number 4, that's tough. That's about as hard as they'll get. Okay, start with grams to get to grams of something else, and we always have to go through moles, and so that's what I had to do there in the middle. Complete the following mole conversions. Okay, we're in the home stretch, guys, which is good news for me because I'm ready to be done. So let's see what we got here. Mole conversion. Starting with number 1, we have 77.6 grams of calcium carbonate. All right, so I'm going to start with that. 77.56 grams CaCO3, and we want to find out how many moles that is. So my conversion factor is going to put grams on the bottom, it's going to put moles on the top, and just like what we did in the last problem with iron 3 oxide, we have got to figure out what is the molar mass of calcium carbonate. So I don't know, I got a little bit of room over here. We have 1 calcium, so I'm just going to say, well, calcium is 40.08. It's not one I have memorized, grams per mole. And I have carbon, 1 carbon, so that's just going to be 12.01. Okay, not multiplying by anything because there's only 1 of them. And then we have 3 oxygens. So 3 times 16. I'm going to add all that together and see what we get. Alright, and I get 100.1. Let's just call it 100.1 grams per mole. So that is going to go right there. 100.1 grams of calcium carbonate for every 1 mole of calcium carbonate. And as we can see, because of the way I've set up my conversion factor, grams gets canceled and we're left with moles. So I'll just do 77.56 divided by 100.1 and I get a number, 0.77 moles. Alright, moving on to the next one. I'm just going to keep on rolling. Number 2, it says, look, you start with moles this time. So they flipped it on us. 0.0931 mole of barium chloride. And we want to find out how many grams that is. So I'm going to set up another conversion factor. But this time, I want moles to go on the bottom. Okay? And I want grams to go on the top. Because I want to cancel the moles. I don't want to cancel grams. So, to do this, same thing as before. Sorry, this is 1 mole. Duh. But we're going to do the same thing. We have 1 barium. Barium is right here, 137.38 grams per mole. There's only 1 of them. And we have 2 chlorines, and that's 35.45. Okay. So, I'm going to add all that junk together. 0.38 plus 2 times 35.45. Alright, and I get 208.3. Alright, 208.3 grams per mole. So, it's going to go right here. There we go. What a great 8 I just drew. Alright, so again, same as before. 0.0931, except this time I'm going to multiply by my 208 number and divide by 1, and I end up getting 19, let's just call it 19.4 grams. Alright, we can see, look, moles canceled. We were left with grams. It worked out beautifully. Let's take a look at number 3. Number 3, we have moles of HF, and we want to find out how many molecules that is. Now, this is where you have to use Avogadro's number, the one that everybody looked up on Google for their quiz and got the wrong answer because you just wrote down what Google said. Avogadro's number. Is 6.022 times 10 to the 23rd. 23 what? Well, that means particles. That means molecules. That means atoms. Whatever. Per 1 mole. That many in 1 mole. Avogadro's number is the one that I use the example of eggs in a dozen. Okay, eggs in a dozen. Well, there's 12 eggs in 1 dozen. Well, there's 6.022 times 10 to the 23rd atoms in 1 mole of something. So that's how we're going to use that. So coming back over here to this problem, we start with 0.664 moles of HF. We want to find out how many molecules it is. So I'm going to put moles of HF on the bottom. And so this is going to be equal. 1 mole of that is going to be equal to 6.022 times 10 to the 23rd molecules of HF. And that's how you use it. That's it. 1 to 1. Okay? This is equal to this, to 1 mole. And so we can use a conversion factor just like this. So I'll tell you, all right, 0.664 times 6.022 second E, I'm using the little E symbol, to the 23, and I get 4, basically. No, I'm just kidding. 4 times 10 to the 23rd molecules, which is a lot of molecules. That's a lot. Alright, moving on to number 4. Number 4 is very similar, it's just flipped. Okay, so number 4, we're starting with molecules. Okay, in fact, I'll go ahead and write that down. 1.55 times 10 to the 26th molecules. It's not telling us what it is because it doesn't matter what it is. Okay? Doesn't matter if it's brown eggs or white eggs or, you know, what is it? Free-range organic farm eggs. It's still eggs. 12 is equal to a dozen. These molecules are still going to be equal to 1 mole in terms of Avogadro's number. So 1.55 times 10 to the 26 molecules set up my conversion factor. I want to get rid of molecules, so I'm going to put that on the bottom, and I want to get mole, so I'm going to put that on top, and again, use Avogadro's number. Okay. So, in my calculator, what I'm putting in is I'm doing 1 point, in fact, I'm going to use parentheses, 1.55, second e to the 26, close parentheses, divided by, parentheses, 6.022, second e to the 23rd, close parentheses, and I end up getting 257.4 moles. That's a lot of moles, okay, but it works. All right, it just works. All right, let's take a look at number 5. 5 and 6 are both using the same idea. Okay, these are both using the same idea. If you look on your reference table, in fact, I'm going to read it word for word. On the very first page of chemistry reference table, it says volume of 1 mole of any gas, STP, okay, is equal to 22.4 liters. I'm going to use that same relationship for 5 and 6. Any gas. So let's do that. I'm going to start with 58.4 liters of CO2. And so I need to put, well, 22.4 liters on the bottom in 1 mole of CO2. And if you guys don't remember, STP just means standard temperature and pressure. Standard temperature is, it depends on where you look, but usually 25 degrees Celsius. Pressure, 1 atmosphere. 1 atmosphere pressure. So in other words, the pressure at sea level. Okay, standard pressure. Alright, so I'm going to use this conversion factor. Look, liters cancels. Liters, and we're left with moles. So I'll say, alright, 58.4 divided by 22.4, and I end up getting 2.61. So I'll write that down. Boy, that was difficult. Number 6, same thing, but the opposite. Because now they're starting us with moles. So 2.5 moles of O2, and we want to find out how many liters. So I'm going to put liters on top. I'm going to put moles on the bottom. And look, 1 mole is equal to 22.4. So I can say, well, 1 mole, 22.4 liters. Alright, so I do 2.5 times 22.4, and I end up getting 56 liters. That is a lot of 2-liter bottles. Alright, there you have it. Alright, we're almost done. Whew, hallelujah. Alright, solve the following formula problems. Be sure to show your work. Oh, I will. Worksheet. Because I always show my work. And I gotta say, guys, if you're that student that's just writing in like random numbers with no units, or worse, you just write a final answer and think that's good enough, ooh, you're going to be really, really upset when you get a bad grade. Excuse me, let me get some drink. So make sure you're showing your work. All right, calculate the percent composition of K2CO3. I will. So first things first, we need to find the total empirical molar mass for this. So we need to find what is the molar mass of all of these things, because we're going to need that for this part of the problem. Because the thing is, if you're doing percent composition, you're doing part divided by whole, and so if we know what the whole mass is of potassium carbonate, then we can divide the little parts, and it's going to be okay. All right, I'm going to set it up. I think I'm going to set it up this way. We'll start with 2 Ks. All right, let's start with 2 Ks. So that's going to be 2 times K. Let me go back to the periodic table. 39.10. Okay, this is grams per mole. And I'm also going to have 1 carbon. So this is just going to be equal to 12.01. And then I'm going to have 3 oxygens. I think it ends up equaling 48, but I don't remember. Yeah, it is. Alright, 48 grams per mole. Oh, I forgot potassium. 2 times 3, 9.10. This is going to make sense here in a second. So, the thing is, I can add all this up and end up finding out what the total amount is. In fact, I think I'm going to do that really quick. And I get 138.21. And 138.21 is great, but that's not what it's looking for. Hey, Cameron, long time no see. So here's the thing. We have this total amount down here, but that's not the answer. We want the percent composition of each. But what I can do now is I can use this for each of these and divide it out. Now, before you start saying, because I know what you guys are going to say, you're going to say, well, for carbon that makes sense. You have one carbon, and you're dividing by 138.21. And by the way, we're also going to multiply this by 100%. This is percent composition after all, so we are going to end up multiplying by 100%. But the thing is, if you say, well, why wouldn't we just do one potassium? Because there's not just one potassium, there's two potassiums here. Why wouldn't we just do it for one oxygen? Because there's 3 oxygens in this. Okay? If you're getting one of those cheesecake samplers, okay, which I really want, I should probably go get one. I'll risk the stay home, stay safe for cheesecake. But if you ever had one of those cheesecakes where it's like 1/4 of it is cherry, or like strawberry swirl, and 1 part of it's caramel, and 1/4 of it is chocolate, and 1/4 of it is just plain white cheesecake. The thing is, even though there's 2 pieces in that 1/4, you're still going to count it as 1/4. You're not going to count it as 1 piece because there's 2 pieces of it. I don't think this cheesecake analogy is working. I'm just really hungry. I need to eat some lunch here in a second. Alright, so anyway, this is going to work, and so we can find our percent composition for carbon by saying, oh, well then 12.01 divided by 138.21 times 100, and I find out that this is 8.69% carbon by mass. That's really how we describe this. That's by mass, because we're doing grams per mole. Do the same thing with potassium. Now, I'm going to divide this by 138.21. Look, we're doing part divided by whole, okay, times 100%. That's all we're doing here, because that's how percentages work, y'all. All right, so divided by 138.21 times 100%. Let's see what we get. 78.2 divided by 138.21 times 100, and I get 56.6% potassium. Okay, do y'all kind of see how this is working out? Cameron, I read an article yesterday that was saying that coronavirus is not really transmitted through food, because if your food does have coronavirus bacteria on it, as long as you eat it, and you just eat it, it actually gets digested in your stomach acid. So like the bacteria, the virus bacteria, does get digested. So I think you're good. That's why I ate fast food last night. I went to Wendy's. It was okay. So what I'm trying to say is just eat the coronavirus. All right. So 48 divided by 138.21 times 100% again. And so, all right, 48 divided by 138.21 times 100. And I get 34.73. But you know what? We'll just make it 34.7% oxygen. Now, here's the thing, y'all. Here's the thing. If you add all of these up, you better hope that you get 100%, because if not, you've done something wrong. Okay, percentages should add up to that. Now, yeah, if you get 99.99%, that's still 100. But if you ever get something that's not 100, you've done something wrong. Okay, so I showed my work. I'm going to put a box around my final answer over here, okay, of all my percentages, and I'm going to go on to the next one. Next one's kind of funky. I'm going to zoom out a little bit. It says, given a 50-gram sample, okay, bat soup. Oh my goodness, are you serious? Well, I'll have to pop over and watch that here in a second. So anyway, all right, focus, guys, laser focus, because I got to eat soon. So given a 50-gram sample of the compound, how many grams of each element would you have? So what you've got to consider is this. If it were just a 100-gram sample, you would say, oh, well, then it's 56.6 grams potassium, 8.69 grams carbon, and 34.7 grams of oxygen. But the thing is, that's not what we're dealing with. We're dealing with a 50-gram sample. So the easiest way to explain this to y'all is if you look up here, 56.6 is the same thing as saying 0.566. Okay? That's the same thing. Or, same thing as saying 0.0869. So obviously 0.347. Okay? I had to do some math last night because I was looking at decking material, and I was like, well, if I want to get 10% more of what I currently have, I'll just multiply by 1.1. And so if I said, well, I need 700 square feet times 1.1, oh, I just need to order 70 extra square feet. So by using these decimal forms, so this is a percentage form, this is a decimal, okay? By using the decimal, you can just multiply that by something and it'll tell you what fraction you need. So what that means is down here, if I say, all right, I got 50 grams, all right, well, 50 grams, I'll do it in order, KCO. 50 grams times 0.566. I'm going to do again, 50 grams times 0.0869, and I'm going to do 50 grams times 0.347. And the thing is, by doing all of this, it should end up working. In fact, I'll show you. We can prove it here in a second. 0.566 times 50, I get 28.3. That's grams still. So 28.3 grams of potassium. I'm going to do 50 times 0.0869, and I'm going to get 4.345 grams of carbon. And I'm also going to do 50 times 0.347. And I get 17.35 grams of oxygen. Now here's the thing, y'all. Okay. Oh my goodness. 4 cups of coffee. Alright. All of these should add up to 50 grams. That's the way that you can make sure that you've done this correctly, because everything should add up to 50 grams. Alright, come on now, OneNote. You can do it. Load what I just wrote. Load what I wrote. You can do it. Or not. There we go. Alright, let's take a look at number 3. Our answer, by the way, it's right here. That's how many grams of each element we would have. Laser focus, guys. Number 3. A sample was analyzed and found to contain 40% carbon, 6.71% hydrogen, and 53.29% oxygen. What is the empirical formula? So it's a hard cut now. We're moving on to a new compound in number 3, and we're going to use that compound for number 4 as well. All right, so let's start with number 3, and let's just see what we get. Samples analyzed. All right, an empirical mass problem. Empirical formula problem. I've told you we did it in the Bellwork. You're always going to start by first doing percent to mass. That's step 1. Percent to mass. So literally, all I'm going to do is I'm going to write all these numbers we just got. In fact, you know what? I think I need a little bit more room. I'll squeeze it in. It'll be okay. I'll squeeze it in. Percent to mass is step number 1. Scoot over the camera. There we go. And so, I'm going to say, well, instead of writing these percentages, I am literally just going to write them as masses. So yeah, I know I got 40% carbon. I'm just going to make it 40 grams of carbon. Okay? Because I can. Next, I know I got 6.71% hydrogen, but now I'm going to make it 6.71 grams of hydrogen. And then last but not least, I'm going to have 53.29 grams of oxygen. So I'm literally just taking all those percentages and I'm just writing them out as grams. And hopefully my internet... Oh, I know why the internet dropped. My wife is doing she's doing a meeting, a Zoom meeting with her school in the other room. So that's probably why it's gone all slow all of a sudden. That's annoying. So, next. I know it'll load in a second, guys. What I'm doing is I'm writing on my iPad like I normally do, and then it updates it and sends it to my computer, and it has been working fine, but now our internet's being strained a little bit. So it'll load here in a second. Step number 2. Okay, we've done percent to mass. Step number 2 is going from mass to mole. Okay, step number 2 is going to go from mass to mole. And so, I'm going to do that by using the periodic table. So, I'm going to say, well, I don't want grams of carbon anymore. I want moles of carbon. Okay? I don't want grams of hydrogen. I want moles of hydrogen. So, I'll do that here. And finally, I don't want grams of oxygen. I want moles of oxygen. So, as you can see, I'm writing everything out so that we can do that. We already did a couple Zoom meetings earlier on in the quarantine, Cameron. Alright, needed some more cheer wine. Today's sponsor, cheer wine. Alright, so all this comes from the periodic table. 12.01 grams of carbon is equal to 1 mole carbon. 1.008 grams of hydrogen is 1 mole of hydrogen. And 16.00 grams of oxygen is equal to 1 mole of oxygen. So all of this is coming from the periodic table. And the reason I switched from Zoom meetings was, it's not that it isn't great to see all your smiling faces, but the fact is, it's so much easier to do it to YouTube because it saves automatically. I can just share the video with anybody, and they can go back and re-watch it if they missed the meeting. So this has just been better for me. If it's really important to y'all, you know, you can, if enough of you email and you want to do a Zoom meeting, maybe we can do it, but we'll see. Alright, so we got all this junk. We need to actually do a little bit of math real quick. So I'm going to say, alright, 40 divided by 12.01, 3.33. And this is now going to be moles of carbon. Alright, and if you don't believe me, look, grams cancels, and we're left with moles. Oh my gosh, I hope so. Alright, next, we're going to have 6.71 divided by 1.008, and I end up getting let's just call it 6.66. Oh, shoot. There we go, moles of hydrogen. The next one, 53.29 divided by 16, and I get 3.33. Hey, this is looking to be very promising. We're gonna go somewhere with this. So now that we have this, let's go to step number 3, which I hope you guys see. I'm writing them over here to the side. This is all coming from that poem. Percent to mass, mass to mole, divide by small, and then step number 4 is multiply till whole, which I don't think we're going to have to do here. So divide by small. My smallest number is 3.33, and so I'm dividing all of these by 3.33. If you guys want a better explanation of this, I recommend you watch the beginning of the video where I actually talk about the Bellwork and I go over that in some detail. I think you'll like that a lot better. So we end up getting 1, 2, and 1. Now all of these things, that'll do. That's close. It's not as good. I think cheer wine's a little bit better, but cherry Coke's pretty good. I tried cherry vanilla Coke Zero recently, and it was pretty good. All of these are ratios. You use this in the chemical formula, because the thing is, up until this point, you know we got carbon with something written below it. We know we have hydrogen with something written below it. And we know we have oxygen with something written below it. Okay? But that's where all these numbers go. So now that we have these numbers here, okay, that's what goes in these blanks. So we can say, oh, well, this is a 1, so we're not going to write it at all. Okay, this is a 2, so I'm going to put that there. And this is a 1, so we're not going to write it at all. So all this, exactly, all of this was just to get CH2O. So that's my answer. I'm going to rewrite it down here. And that may seem like a lot of work, but that's it. And notice, we didn't need to use step number 4. We got nice whole numbers, 1, 2, and 1, so we didn't have to multiply till whole. But sometimes you do. Again, go look at the Bellwork that I went over at the beginning of the video. Problem number 4. Given the molecular weight of the compound in problem 3 is 180.16 grams per mole, what is the molecular formula of the compound? First thing that we're going to do, and I've already talked about it earlier today, but there is a formula for this. You're always going to do your experimental molar weight, okay, divided by your empirical molar weight. That's always the formula that you're going to use. So experimental molar weight, they just gave it to us. They said, well, it's 180.16 grams per mole. But the empirical molar weight, we got to do just a little bit of work with. So we look at our formula, okay, CH2O, and we can say, well, this is 1 times 12.01. Hydrogen is going to be 2 times 1.008. And then oxygen is going to be 1 times 16.00. All right, we'll add all this together, and we'll have a number here in a moment. And we get 30. Just 30.0. Let's just keep it easy. So that number goes right here. And so obviously when you divide these, 18 divided by 30 is a number 6. There we go. 6. That is not the answer. That is not the answer. That's useful. It's going to help us. But that tells us what we need to multiply everything by so that we do get the answer. So from before, we have CH2O. This is our empirical formula, okay, CH2O. But now what we're going to do is we're going to multiply everything by 6, not 2. Why did I write a 2? Everything by 6 down below, all these little subscripts, so that we get the new molecular formula. So what we end up getting is C6H12. That looks terrible. There we go. O6. So this is the molecular. And that's all there is to it, y'all. That is all there is to it. All right. And that is the whole daggone review. So, we're done. Your test is tomorrow, in case you didn't know. So if you have any questions for me, now is the time to ask. Because I'm about to end the stream here in a minute and probably eat a sandwich and dream about cheesecake. But if you have any questions, now is a good time. Or just tell me how you guys are doing. Are you doing all right? Are you staying healthy? Are you eating enough? Are you trying to get outside a little bit while social distancing? Okay, how are you guys doing? I'm serious. I'm concerned for y'all. The 5 of you that are in the stream. I guess you all left. You said, well, I got the answers that I wanted. I'm leaving. Okay, well, it was worth a shot. I just wanted to see how you guys were doing. Take care of yourselves. If you need anything, please text me. Remember, Unit 4 review and vocab are both due tomorrow. Cameron, do you have Remind? Cameron and Emily, if you're both, well, Tess, staying up late at night and watching YouTube's not going to help you. Oh, Lord. Cameron. Ugh. All right. Cameron and Emily both, if you haven't texted, y'all are both my seniors, text me on Remind. I want to share something with y'all. But otherwise, I think we're going to be okay. Tess, don't stay up so late at night. Try and get on a regular sleeping schedule. Think about it this way. If you go to bed early, you can get up early and get your schoolwork done, and then you watch YouTube videos at a normal time. It's just something to think about. Just something to think about. Okay, well, Cameron, email me. I want to share something with you. But we'll do that outside of the YouTube. Okay, guys, take care of yourself. If you need anything, you know where to find me. I'll put information about submitting the vocab and this assignment tomorrow. But remember, if you don't have the OneNote app on your phone, highly recommended so that you can take pictures of your work a lot easier. All right, guys, as always, be proud to be a Jet. I want to thank our sponsor, Cheer One. Thanks for liking, subscribing, and clicking that bell so that you can get all the videos instantly. Appreciate you guys. Take care of yourselves. Have a good one.